Hello everyone, and welcome to our video on oxidation-reduction reactions. An oxidation-reduction reaction is a reaction in which there is an exchange of electrons between your two substances. So just to give you an idea of what I'm talking about, we're going to start with a really simple example. Let's look at magnesium plus oxygen goes to magnesium oxide. Okay, now with this reaction, if you know your rules for oxidation states, you know that any substance in its pure form has an oxidation number of 0. And so in this case, magnesium is in its natural alone state, so that has an oxidation number of 0. Oxygen is in its natural unbonded state, and so it has an oxidation number of 0 as well. However, when we look over here at the right side of the equation, we see that we have one magnesium bonded to one oxygen. So if we look at our oxidation number rules, which we will go over in another video, if you're not familiar with those, you know that oxygen has an oxidation state of -2. So that means that by extension, our magnesium has to have an oxidation number of +2. So the question here becomes, what happened? What changed so that the magnesium went from 0 to a 2 and the oxygen went from a 0 to a -2? Well, we can see that there was an exchange of electrons. So what we do is we break this down into two half reactions. For one of the reactions, I'm going to pull up another color here, we say that magnesium went to magnesium 2 plus 2 electrons. And for the other half reaction, we say that oxygen plus 2 electrons turned into oxygen with a -2 charge. So that's what an oxidation reduction reaction is. It's two half reactions, one being oxidation and the other being reduction, that together form one complete oxidation reduction reaction. So the question becomes, what does oxidation mean and what does reduction mean? Well, there's a few ways that you can remember this. And I've actually drawn a lovely picture here. As you can see, I'm basically a professional artist. But the mnemonic here is Leo the lion says grr. And what this stands for is, I'm just going to go ahead and draw this out. Leo stands for loss of electrons is oxidation, while grr stands for gain of electrons is reduction. And so that's what the oxidation and reduction stands for in an oxidation reduction reaction. Oxidation is oxidation is a loss of electrons, whereas reduction is a gain in electrons. So if we come back here to our chemical reaction that we're looking at, what gained electrons? So what we can say over here is we can say oxygen. Well, what happened to oxygen? Oxygen gained electrons. And what's gain? Gain is reduction. So oxygen was reduced, which means that magnesium was oxidized. And why was it oxidized? Because it lost electrons. Now there is another mnemonic to remember this if you prefer. Another mnemonic, although I don't know why you would need another with my beautiful lion drawing here. But if you don't like Leo the lion says grr, you could also remember oil rig. Oil rig stands for oxidation is loss, whereas reduction is gain. So whatever works for you. You can think of oil rig, oxidation is loss, reduction is gain, or you can think of Leo the lion says grr, loss of electrons is oxidation, gain of electrons is reduction. Now, I actually learned oil rig before I learned Leo the Lion Says Grr. So to be honest, oil rig often is the first thing that comes to my mind. But I really like this mnemonic of Leo the Lion Says Grr because it actually says electrons in it. And so I've heard of people with oil rig, sometimes they start to think, well, wait, gain of what, loss of what? So that's the nice thing about Leo the Lion Says Grr is that it actually says right there within the mnemonic, electrons. So you never have that small chance of forgetting, well, what are we referring to? It's actually the electrons to which we're referring. So let's go ahead and take a look at another example. So I'm going to go ahead and clear us some space. So in this example, let's say zinc plus hydrochloric acid goes to hydrogen gas plus zinc chloride. Okay, so looking back to our oxidation state rules, we know that anything in its pure state is going to be just an oxidation number of 0. And zinc is obviously in a pure state here, so we can say that it has an oxidation state of 0. Now over here in hydrochloric acid, this obviously is not a pure state. This is two different elements bonded together. So going back to our oxidation rules, which again, if you're not clear on, I'm going to make another video on those later, so you can always check out that video. Let's see. So in this, the chloride is the first thing that we're going to look at. This being in the seventh period, or excuse me, the seventh row is going to have an oxidation state of -1, which means that hydrogen, since it's bonded to a nonmetal, will have an oxidation state of +1. Now over on the other side of the equation, this is obviously a 0 because it's by itself, it's just hydrogen, a pure element. But if we look over here, we know that there are 2 chlorines. Now each chlorine is going to have an oxidation state of -1, which means that altogether, because you have to remember this is added together, this is a compounding effect, since there's 2 of them, the overall oxidation state is -2, which means that the zinc now has an oxidation state of +2. You follow? So if we come down here and take a look at what exactly is going on, well, we know that we need to set the oxidation and reduction for both things on the left side of the equation. So zinc started at 0 and it ends at +2. You see that? Because zinc right here has 0 and zinc right here has +2. So it's safe to say that zinc, having lost electrons because we went from 0 up to +2. Now remember, if the charge goes up, then you're losing electrons because electrons have a negative charge. So losing that negative charge will make you more positive. Okay, so zinc was oxidized. And if you have trouble picturing why that is, then you can think of a number line. So let's just draw a quick line right here. Let's say that this is 0, okay? Now, think of this over here as being number of electrons on the left side. Number of electrons. Now, if you start with a given number of electrons, which would be X, that given number of electrons would give you an oxidation state of 0. Your protons and your electrons are perfectly balanced, which means that your net charge is 0. But if your number of electrons starts to go down, so X -1, X -2, X -3, you're losing electrons. And if you're losing electrons, then that means that you have less negative charge. But the only thing that you're losing is electrons. You're not losing protons. So if you're losing electrons, but you're not losing protons, that means that as you lose those negative charges, your net charge will increase. So +1, +2, +3. See that? But if you begin to gain electrons, X +1, X +2, you're now increasing the amount of negativity that you have. But again, your protons are not changing. If you're an atom and you have a set number of protons, those protons don't change. The only thing that's changing is your number of electrons. So as you gain electrons, you're also gaining more net negative charge. So as your number of electrons go up, your net charge goes down. So hopefully that clears that up if you've struggled with that concept at all. So as your number of electrons goes down, or as you lose electrons, your charge will go up. And that's exactly what's happened to zinc here. Zinc lost 2 electrons, which means that it gained a positive 2 charge, which means that it was oxidized. Make sense? Oil rig. Oxidation is loss. Leo the Land says grr. Now the other element that we have to look at here, we have to look at HCl, or looking at our Cl. So Cl went from -1 to -1. Oh, so Cl didn't change. Okay, so what did change? Well, let's see, what else do we have? Well, we have hydrogen right here. Hydrogen was at +1, and now it's at 0. So what happens if your net positive charge decreases? Yeah, if your net positive charge decreases, then your number of electrons increased. So hydrogen was reduced. Does that make sense? And the reason that we can say that nothing happened to the chlorine is because it went from 0, or excuse me, it went from -1 to -1, or in other words, it didn't change, which means that the 2 elements that did change within this oxidation reduction reaction are zinc, which was oxidized, and hydrogen, which was reduced. So now that we have the basics of oxidation reduction reactions down, let's take a look at some more complete examples, because the ones that we've done so far have been really simple, very narrow in their scope. So let's take a look at some types of questions that you might actually see on an exam. So on this first example right here, we have chromium acetate plus zinc metal goes to chromium plus zinc sulfate. So in this problem, what we need to find is how many electrons were transferred. Now you'll notice in this problem, not all of the elements are here. So if not all of the elements that we need for this entire reaction to take place are given to you in the problem, that's a pretty safe bet that you don't have to actually balance the equation, okay? And what I mean by that is, you'll notice that we have sulfate right here, and sulfate obviously involves sulfur. But if we look at the left side of the equation, you'll find that there's no sulfur here. And so what that means is that in this problem, we're not looking to balance it entirely. We're just trying to figure out, okay, what changed electrons and why did those electrons change? And how many of those electrons were changed? So the place to start is to take a look at your oxidation states. Now we know that the oxidation state of sulfate, excuse me, not sulfate, the oxidation state of acetate is -1. And we have 3 of those acetates. So remember, it's an additive effect. If the acetate has an oxidation state of -1 and there's 3 of them, that means that the overall oxidation state of the acetate is -3, which means by extension that the oxidation state of our chromium is +3. Because as you can see from right here, there's no net charge on this molecule. This is a neutral molecule. So if the acetate has a -3, then the chromium has to have a +3. And remember, per our oxidation state rules, zinc, being a pure element, has an oxidation state of 0. Moving on to the right side of the equation, we can see that now chromium has an oxidation state of 0 because it's by itself. Whereas the zinc sulfate, well, what do we know about sulfate? We know that sulfate has a charge of -2, and there's only one sulfate, right? There's no additional subscript, which means that our zinc has to have an oxidation state of +2, okay? So let's go ahead and write out these half reactions so that we can get a better idea of what's going on. We know that the zinc on the left side of the equation was just by itself, so we don't have to do anything else. We just say that zinc goes to zinc 2 positive, and that means that it lost electrons. So we have zinc goes to zinc 2 positive plus 2 electrons. And we also know that chromium on the left side had a net charge of +3. But on the right side, it's going to chromium 0. So that means that we have to add something on the left side of the equation. Well, we obviously have to add 3 electrons, because if its oxidation state was 3 positive, then it's going to take 3 electrons to bring it to a neutral state. But looking at these two half equations, you should notice there's a problem. Up here, we have 2 electrons. Down here, we have 3 electrons. That doesn't match. So what we have to do is we just look for the least common denominator of 2 and 3. And the least common denominator of 2 and 3 would be 6. So all you have to do is you multiply each half reaction by whatever it takes to get it up to that least common denominator. So we're going to multiply this top portion by 3, and we're going to multiply this bottom portion by 2. And what that's going to give us is 3 zinc goes to 3 zinc ions plus 6 electrons. And on the bottom, we're going to get 6 electrons plus 2 chromium ions goes to 2 chromium neutral. And you'll notice now our number of electrons actually matches. So, bottom line, we didn't have to completely balance the initial equation because not all of the information was given to us. That sulfate or the sulfur has to be coming from somewhere. Obviously, the oxygens didn't match. So we know that for this type of test question, we're not trying to balance out everything. All we're trying to figure out is, okay, how many electrons were transferred all in all? And as we can clearly see from balancing the half reactions, there was a net transfer of 6 electrons. So that's how you would handle this kind of problem. Now, let's talk about the final type of oxidation reduction reaction question that you're likely to encounter on a test. And that is to actually completely balance the oxidation reduction reaction. So the difference here, as you just saw in that example, we didn't have to completely balance the entire reaction. We just had to figure out how many electrons were being transferred. But for this final type of problem, we actually need to completely balance the entire equation in addition to figuring out how many electrons were transferred. Now, in order to figure out how to balance the entire reaction, there's one last piece of information that we need, and that's whether this oxidation reduction reaction is taking place under acidic conditions or whether it's taking place under basic conditions. And the reason for that is that under acidic conditions, you're going to have a bunch of hydronium ions floating around, right? And those have a net positive charge. However, if you're under basic conditions, you're going to have a bunch of hydroxide or hydroxyl groups floating around. And those have a net negative charge. And so if you're transferring around electrons which have a negative charge, obviously you're going to be affected by whether you have ions with a positive or a negative charge floating around in that aqueous solution. So to completely balance an oxidation reduction reaction, the way that you know if you have to completely balance everything is if in the problem you're told that you're balancing under acidic or under basic conditions. So let's take a look at this next problem. We have MnO4 plus Cl negative goes to MnO2 plus Cl2. Okay. So first thing that we're going to do is we're going to balance this under acidic conditions, and then we're going to balance it under basic conditions. So the very first thing that we're going to want to do with this problem is just figure out what our half reactions are again, because that's step number 1, identify and separate oxidation and reduction agents. Okay, so pretty straightforward, just like we did before. Let's figure out what's being reduced. Okay, so starting out, we know that the oxidation numbers on oxygen are always going to be numbered -2, unless, of course, it's a peroxide. Just remember, oxygen is almost always -2 unless it's in a peroxide, in which case it's -1. Now, since these are additives, since we have 4 oxygens and they have a charge or an oxidation state of -2 each, total we know that the negative charge here is 8, which means that the manganese normally would have a charge or an oxidation state of 8, positive. However, look right here, we have a total net negative charge here because this is an ion. So the 8 won't change on the oxygen. What can change is the manganese. So the manganese actually has an oxidation state of 7, not 8. The chlorine obviously has an oxidation state of -1, since we're dealing with a chloride ion. On the other side, we have oxygen, not a peroxide, so we know that it has an oxidation state of 2, negative, and there's 2 of them. So total, we have 4, which means that the manganese on this side has a +4. And then, of course, chlorine is going to have an oxidation state of 0 since it is not an ionic chlorine entity. So to split these into half reactions, let's take a look at what is oxidized and what's reduced. Manganese goes from 7 positive to 4 positive. Now, if its positive state is being lowered, that means it's being reduced, right? It's being reduced, which is gaining electrons. It's reduced from 7 to 4, which means it gained electrons, which means it's being reduced. So let's go ahead and throw that right here. MnO4, 1 negative, going to MnO2. And that is reduced. Okay, let's take a look at our chlorine. Chlorine right here is negative, and that's going to Cl2. That is being oxidized. Okay, so going back to our steps, step number 1, identify and separate oxidation and reduction agents. Okay, done. Step number 2, balance all non-oxygen and hydrogen reagents. Okay, let's balance these. Manganese, that looks pretty balanced to me. 1 manganese on the left side, 1 manganese on the right side. What about our chlorine? Well, we have 1 chlorine on the left, 2 chlorine on the right. That's not balanced. So we're going to have to throw a 2 in front of the chloride ion right there. Okay, so balance all non-oxygen and hydrogen agents. Done. Step number 3, balance oxygen with H2O. Well, for chlorine, I don't think we have to worry about that. There's no oxygen anywhere. However, in the first half reaction, we have 4 oxygens on the left side, but we only have 2 oxygens on the right side. So we're going to have to do something about that. I'm going to scoot this over a little bit, give us some more room. Okay, so in order to balance this, we're going to have to add 2 H2O to the right side. And you see that by adding 2 H2O, we have 2 oxygens plus 2 oxygens equals 4 oxygens. Now we have 4 oxygens on each side of that equation. So step number 3 done. Lastly, balance hydrogen with hydronium ions. Okay, well, on the right side of the equation, we have 4 hydrogens, but on the left side, we don't have any hydrogens. So we're obviously going to have to add 4 H plus to the left side. So now we should be completely balanced. We have 4 hydrogens on the left side, 4 hydrogens on the right side, 1 manganese on the left, 1 manganese on the right, 4 oxygens on the left, 4 oxygens on the right. So it looks like we're all balanced up. Now, up to this point, whether we're balancing under acidic or basic conditions, these steps are the same. So anytime you're given one of these problems, doesn't matter what conditions you're in, you'll do up to this point the same regardless. But at this point, we're going to handle things differently. So it's at this point that you need to identify in your original question whether you're being asked to balance the equation under acidic or basic conditions. And for this video, we're just going to go ahead and do both. So let's do acidic first. So under acidic conditions, add electrons to balance the charge. So in this first half reaction, we know that we have a 1 negative right here, and we have 4 positives right here. Don't forget that the stoichiometry, each hydrogen only has a positive charge, but we have 4 hydrogens, which means that the total net charge that we have on the left side of the equation here, that total net charge, I need another color. Let's do orange. That sounds good. The total net charge on this side of the equation is 3 plus. Now on the right side of the equation, that total net charge is 0. So in order to balance things out, all we need to do is add 3 electrons to the left side of the equation. And by adding 3 electrons, that's going to balance out this 3 positive charge. And now the net charge on both sides of the equation for the first half reaction is 0. Now for the second, we have a 2 negative charge on the left side and a 0 charge on the right side. So to get this balanced up, we just need to add 2 electrons to the right side of the equation. Now, let's step back and take a look and see where we are. We have our reduction half reaction right here, and we have our oxidation half reaction right here. And that makes sense, right? Because reduction is gaining electrons. And so anytime that you have reduction, you know that you're going to have electrons on the left side of the equation, right? Because if you're gaining electrons, it's going to be on the left side that you're gaining those electrons and you're adding them into the equation. Now for oxidation, you're always going to have your electrons on the right side of the reaction because oxidation is loss. So whatever is on the left side of that equation is losing electrons. And if it's losing electrons, that means that the electrons are going to be reflected on the right side of the equation. So let's check and see if we're balanced. Okay, so we have 3 electrons right here on the left side of the equation. And we have 2 electrons right here on the right side of the equation. So is that balanced? Absolutely not. All we have to do is multiply to reach the greatest common factor or the lowest common denominator of each of those numbers. So all we have to do is multiply the top equation by 2, multiply the bottom equation by 3. Okay, now once we've multiplied those out, we're going to get 6 electrons plus 8 hydronium ions plus 2 manganese oxide, 1 negative, goes to 2 MnO2 plus 4 H2O. And then down here, we have 6 chloride ions goes to 3 Cl2 plus 6 electrons. And now, as we can clearly see, we have 6 electrons on the left, 6 electrons on the right. So that's exactly where we want it to be. Now, at this point, since we're going under acidic conditions, we added electrons to balance the charge, and we added integers to the half reactions to the point that they were the same. So all we have to do now is add these together, and that's our final balanced reaction under acidic conditions. So to add these up, really what we get, is 6 electrons plus 8 hydronium plus 2 MnO4, 1 negative, plus 6 chloride ions goes to 2 MnO2 plus 4 H2O plus 3 Cl2 plus 6 electrons. And that is our total final balanced equation under acidic conditions. Now, what if we wanted to do the same thing, but we wanted to do it under basic conditions? Well, remember, up to step number 4, it's exactly the same. So to get back to where we were, all we have to do is say 4H plus MnO4 goes to MnO2 plus 2H2O. And then for the second half reaction, we have 2Cl goes to Cl2. Okay, so up to that point, balancing H with hydronium ions, everything is the same. And so that's why I skipped those first 4 steps, just went back here because we already got here when we were doing acidic conditions. This is where it gets different. When you're under basic conditions, the thing to keep in mind is that you don't have hydronium ions floating around in solution. That's the definition of an acidic solution. And so in step number 4, when you're balancing H's with hydronium ions, that's actually not possible under basic conditions. So in order to compensate for that, if you're in basic conditions, you can still get to this point the same. It's a lot harder if you do it a different way. So just come to this point, and then for each hydronium ion added, add a hydroxyl group. So in order to add that hydroxyl group, all we have to do is add, whoops, forgot to switch off of the highlighter. All we have to do is add 4 hydroxyl groups. See? And then we eliminate water. So if we have 4 OH and 4 H positive, that really works out to 4 H2O. Make sense? So let's erase that and make it 4 H2O. And then you add electrons to balance that equation. Oh, excuse me. I forgot to add. Whatever you add to one side, you have to add to the other. And since we added 4 hydroxyl groups to the left side, we also have to add 4 hydroxyl groups to the right side. Okay? And now we eliminate any water there. So if we have 2 waters there, okay, and now we eliminate water. So we have 2 waters right there, so we can also cancel out 2 waters on the left side. So at this point, we can go ahead and add electrons to balance the equation. Well, on the left side of the equation, we have a total net charge of -1. On the right side, we have a total net charge of -4. So how do we balance this out? Yeah, we just go ahead and add 3 electrons to the left side. And then on bottom, we have a total net charge on the left of 2 and a total net charge on the right of 0. So we simply add 2 electrons to the right side. Now, as before, we take a look at each of our half reactions and we check and see where we're standing with electrons. And as you can see, they don't match. So we need to multiply to get the lowest common denominator. That will be 2 on the top half reaction, and that will be 3 on the bottom half reaction. So multiplying that out, we get 6 electrons plus 4 H2O plus 2 manganese oxide goes to 2 manganese oxide plus 4. Oh, we canceled that out. Excuse me. Get rid of that. Plus 8 OH negative. That's our top half reaction. And then on the bottom, we're going to get 6 Cl negative goes to 3 Cl2 plus 6 E negative. And now our electrons match. So to add these together, our final equation is 6 E negative plus 4 H2O plus 2 MnO4 plus 6 Cl goes to 2 MnO2 plus 8 OH negative plus 3 Cl2 plus 6E. So that is how you balance this under basic conditions. So that's going to be it for this video. Thanks so much for watching. And as always, remember, if you have any questions or you'd like to request a topic for a video, go ahead and shoot us a message or leave us a comment down below, and we will make a video for you. Thanks for watching, and don't forget to hit subscribe and like so that we can keep making videos like this. See you next time.